Okay, so this talk is an invitation to explore the learning of adapted kernels for numerical approximation. And to motivate its content, I will start with a few observations. If I were to ask you to solve a PDE 200 years ago, you would probably do it by hand, and you would probably need the expertise of a Cauchy or a Poisson for doing so. If I ask you the same question today, you will use a computer to crunch numbers, but you will still use your brain to find the algorithm for solving the PDE. Question: can you program a computer not only to solve the PDE, but also to find the method or the algorithm for solving the PDE? Well, these three previous slides are taken from a talk given at SIAM in 2015. And although this question was a bit unusual at that time, it is no longer looked upon as an odd question. In fact, there is now a growing interest in using learning techniques to solve differential equations. Now, these learning techniques can be divided into two categories. The first category is composed of kernel methods, which stem from interplays between Gaussian process regression and numerical approximation, and the fact that these two are intimately connected through the process of making estimations with partial information. The second category is composed of variants of artificial neural networks, which stem from the popularity of deep learning and the popularization of automatic differentiation in Python. Although the first approach is by now well understood and has strong theoretical foundations, it relies on the prior selection of a kernel. Although the second approach does not have much theoretical support yet, it can also be understood as a kernel method in which the kernel is also learned from data. And this is something that I will show in this talk. And these observations are some of the motivations for this talk. So I think that most of this audience is already familiar with kernel methods, but to make sure that everyone is on the same page, I will start with a short reminder on scalar-valued kernels in the setting of the following interpolation problem, in which you try to approximate an unknown target function, f dagger, mapping some input space x to the real line, given f dagger of x equals y. Here I write x and y for the n-dimensional vectors whose entries are the input-output data points. And I write f dagger of x for the n-dimensional vector whose entries are the input data points and their f dagger. Now, there are four equivalent ways to describe kernel-based solutions to this problem. And these are based on the four equivalent ways of defining such kernel. The first one is to define a scalar-valued kernel as a function k mapping the input space x times x onto the real line such that for all integer m greater or equal than 1 and all points x1, xm in the input space x, the m by m matrix with entries kxi, xj is symmetric and positive. Now, equivalently, K is a scalar-valued kernel if and only if there exists a Hilbert space F known as a feature space and a function psi mapping the input space X to F known as a feature map such that Kx x prime is equal to the inner product in the space F between psi of x and psi of x prime. Now, this is equivalent to the existence of a Hilbert space of functions f mapping the input space x to the real line such that f of x is equal to the inner product in the space H between f and the function defined by the kernel k supported at the point little x. The norm associated with the inner product in H is known as the RKHS norm associated with the kernel K, and we will also write it as this k-norm for ease of presentation. Now, this is also equivalent to the existence of a centered Gaussian process Xi, such that k is the covariance function of that Gaussian process. Recall that Xi is a function mapping X to a Hilbert space of scalar-valued Gaussian random variables, known as a Gaussian space, and the covariance function of Xi is the function obtained by computing the covariance between Xi at the point x and Xi at the point x prime for all x and x prime. Now, these four equivalent definitions lead to four equivalent solutions to our original interpolation problem. The first one is to approximate the target function f dagger with the following function f, where k is our given kernel, k of capital X is the n by n matrix with the following entries, and k of little x capital X is the n-dimensional vector with the following entries. The second one is to approximate the target function with the following inner product involving the feature map psi associated with the kernel k and some coefficient c living in the feature space f, identified by minimizing its norm subject to the interpolation constraints. Therefore, you can think of kernel interpolation, also known as kriging, as linear interpolation in feature space, and the main idea is to map the data to a Hilbert space via possibly nonlinear feature map, and then to linearly interpolate or approximate the target function in that feature space. The third one is to approximate the target function with the minimizer of the following problem, in which the norm to be minimized is the RKHS norm defined by the kernel K. Recall that since these methods are equivalent, this norm is also defining the kernel K. This approach is also known as optimal recovery in numerical approximation, and it can be traced back to the work of Michelieu and Rivlin. The fourth one is to approximate the target function with the expectation of the Gaussian process with covariance function k conditioned on the interpolation constraints. Now, any non-degenerate kernel could be used to interpolate the data exactly. So one immediate question is, which kernel do we pick? Well, this talk has two main objectives. First, show why this question is important, and second, discuss 5 main answers from the perspective of numerical approximation. The first one is to use prior information on the regularity of the target function to select the kernel, and this is the classical numerical approximation approach. The second one is to use the PDE solved by the target function to select the kernel, and this is the current numerical approximation approach, which is by now well understood when the underlying PDE is elliptic and linear. The third one is the Bayesian approach, and here I will cover maximum likelihood estimation and maximum a posteriori estimation. The fourth one is cross-validation, and the fifth one is deep learning, and it is connected to the Bayesian approach, and this is something that I will show in this talk. So why is this question relevant to numerical approximation? Well, as observed by Sard, Larkin, Diaconis, and many others, who have investigated intriguing similarities between Gaussian process regression and numerical approximation, most numerical approximation methods are actually kernel interpolation methods. For example, the cardinal splines of Schoenberg are optimal recovery splines, i.e. kernel interpolants obtained from 0-1 measurements and defined by polynomial kernels. This is also true for the polyharmonic splines of Owhadi, Desmarais, and Duchon, which can be identified as optimal recovery splines. To describe this, consider the problem of approximating the solution f dagger of the following PDE with an unknown right-hand side in L2. Assume that the values of f dagger are given at these n homogeneously distributed points xi of the domain omega, which I assume to be a subset of Rd of dimension less or equal than 3. Then the polyharmonic spline approximation of f dagger can be identified as the minimizer of the following variational problem, which is an optimal recovery problem. So this minimizer f is a kernel interpolant with a kernel defined by the following RKHS norm. Furthermore, this kernel interpolant is good in the sense that it achieves the Kolmogorov n-width, that is the minimax optimal rate of convergence in approximating f dagger, given that the right-hand side is in L2. Now, this doesn't mean that all kernel-based solutions are good. In fact, if you replace the Laplacian in the previous PDE by a divergence form elliptic operator with rough coefficients, then the convergence of the previous kernel-based method can be arbitrarily bad. Why is it so? This is because the kernel associated with this variational problem is not adapted to the underlying PDE or physics. So what is the solution? Well, it is simply to use a PDE-informed kernel, and this can be done by replacing the previous optimal recovery problem by the following one, in which the quantity to be minimized is the L2 norm of the right-hand side of the PDE. Now, this solution is a Gaussian process regression solution with a PDE-informed prior. This PDE-informed prior is obtained by replacing the unknown right-hand side of the PDE with white noise, and then using the resulting Gaussian process on the solution space as a prior. This approach was called Bayesian numerical homogenization because the resulting prior contains the needed information about the macrostructure of the underlying PDE. Now, the current popular kernel for the numerical homogenization of linear elliptic PDEs is the Green's function of these PDEs. And this is the kernel implicitly used in the variational multiscale and in the LOD methods, and explicitly used with gamblets. So far, the moral of the story is that the answer to our main question, which kernel do we pick, is by now well understood if the regularity of the target function is known a priori, or if it is the solution of a non-linear elliptic PDE. Question: what if the underlying regularity of the target function is unknown? I will compare now the Bayesian and cross-validation answers to that question. And what I'm going to present is based on the following two papers with Jin-Ryan Yu, Yifan Chen, and Andrew Stewart. I will do so in the setting of our original interpolation problem, where we want to approximate an unknown target function, mapping some domain D of Rd to the real line, based on observing the values of the target function at n data points x1, xn. I assume that we are given a family of kernels on that domain D parameterized by some hierarchical parameter theta, and given theta, the kernel or Gaussian process interpolant is then given or represented by the following formula. And the main question that we are going to address is, which theta do we pick? Well, we are going to consider two possible answers to this question. The first one is known as the empirical bias answer. And this answer is to first place a prior on theta, Assume that given theta, the target function is sampled from a centered Gaussian process distribution with covariance function k theta, and then select the theta maximizing the marginal probability of theta subject to conditioning on the values of the target function at the data points. And if we use an uninformative prior on theta, then the resulting estimate is a maximum likelihood estimate obtained by minimizing the following loss function with respect to the value of theta. The second answer, which we refer to as the kernel flow answer, is a variant of cross-validation. And the main idea is to pick a theta such that subsampling the data does not influence the interpolant much. So formally, the kernel flow estimate of theta is obtained by minimizing the following loss with respect to theta. This loss is defined as a relative error between two interpolants. The first interpolant is the interpolant obtained with the kernel k theta and all the data x. The second interpolant is obtained with the kernel k theta and a subset of the data, which we write pi x. So this operator pi is a subsampling operator and pi x is a subvector of x. And the norm used to define this relative error is the RKHS norm of the kernel k theta. So again, the main idea here is that a kernel is good if subsampling has little impact on the approximation of the target function, which is a cross-validation idea in the sense that this relative error acts as a surrogate for the generalization error. Now, we have two natural methods for selecting theta. And the natural question is, what is the behavior of these methods as the number of data points goes to infinity? Well, to answer this question, we are going to consider the following particular model in which the domain is the unit torus of dimension d. The data points are located at the nodes of a regular lattice of resolution 2 to the power minus q, and so we have 2 to the power qd points. The kernel k theta is the Green's function of the fractional Laplacian with power theta with periodic boundary conditions, and our subsampling operator subsamples the points located at the coarser lattice of resolution indexed by q minus 1. Then we have the following theorem. If the target function is sampled from the distribution of a centered Gaussian process with covariance function ks with s strictly greater than d over 2. So here I assume the model to be well specified and the true theta to be s. Then as q goes to infinity, so as the number of data points goes to infinity, then the empirical bias estimate converges to s, and the kernel flow estimate converges to s minus d over 2 in probability. The following figure is a numerical experiment confirming this theoretical result. What you see plotted here are the empirical bias and the kernel flow losses versus theta. For that experiment, the dimension d is 1, s is 2.5, and we use 2 to the power 9 data points. And we indeed see that the minimum is at 2.5 for empirical bias and 1 for kernel flows. So an immediate question is, how are those limits 2.5 and 1 special? And this is related to the implicit bias of these algorithms. The answer is rigorous, but I will illustrate it with two experiments. The first experiment shows the mean square error of the interpolant versus Q, the log of the number of data points, for different values of theta, which is equal to, okay. And what can be seen here is that S minus D over 2, which is equal to 1 for our example, is the smallest theta achieving the fastest rate of convergence in mean square error. The second experiment shows the mean square error of the interpolant versus theta for Q equals 9. And what can be seen is that S, which is 2.5 for our example, is the value of theta achieving the minimal mean square error. So the takeaway message is that empirical bias selects the theta minimizing the mean square error, and kernel flow selects the smallest theta achieving the fastest rate of convergence in mean square error. Okay. Now, one question that may be asked is, why should anyone use kernel flow if empirical bias is optimal in mean square error? And the answer, which I don't have the time to cover here, is that the optimality of empirical bias assumes the model to be well specified. And empirical bias can be brittle, that is non-robust to model misspecification, whereas kernel flows has some degree of robustness to misspecification, and it is also nearly optimal if the model is well specified. And to illustrate this point, I will now consider an example where there is no obviously well-specified model. This example concerns an extrapolation problem in which, given the observation of the time series Z1, Z2, Zn, up to time n, we want to predict the future states Zn plus 1, Zn plus 2, etc. Evidently, to solve such a problem, you need to make some assumptions. And the assumption that we will make is that the Zk can be obtained as the solution of some dynamical system with an unknown vector field f dagger and an unknown time delay tau dagger. As you can imagine, this is a fundamental problem which has received a large amount of attention from the perspective of some wonderful methods, ranging from operator theory to Koopman's sparse approximation to various variants of artificial neural networks. And here, all I want to show you is the simplest possible kernel-based solution you can imagine. And what I'm going to show you can be found in the following paper with Boumediene and Hamzy. So this solution is to approximate the vector field f dagger with a kernel interpolant and then use that kernel interpolant as an emulator. That is a surrogate dynamical system for predicting the future states of the time series. So to implement this method, you give yourself a kernel K, you use the past states of the dynamical system to construct input-output training data, then you interpolate that data with the kernel K to obtain the interpolant of the vector field f dagger. And finally, you simulate the following dynamical system to predict future states. Here, for the sake of time, I'm restricting the presentation to the case where the time delay tau dagger is known. And I refer to this paper for how we learn tau dagger in practice. Okay, so how well does it work? Well, to answer that question, let us look at the following example where the time series is produced by the following Bernoulli map, which is a chaotic dynamical system. And the kernel K is the following Gaussian kernel. This figure shows in red the true dynamic and in blue the predicted dynamic. So it does not work well. Well, let us now add a little twist to this experiment. Let us also learn the kernel K used for creating the surrogate model. What do I mean? Well, for that example, what I mean is that instead of considering a given kernel K, we consider a family of kernels K parameterized by 4 parameters. And we also learn those parameters from data before regressing the target function, the target vector field f dagger. We learn them using the kernel flow algorithm, which I have already described. This figure shows the true dynamic in red and the predicted dynamic in blue, and they are indistinguishable in eyeball norm. Okay, now let us move on to another example. This example is the Henon map, i.e. in this example, the time series that we want to predict is a solution of the following dynamical system, which is also chaotic. And we assume the vector field to be unknown. To predict it, we approximate its vector field by interpolating the past data with this vector valued kernel. This kernel is diagonal, and each diagonal entries is a scalar valued kernel with 6 parameters. And we learn those parameters using kernel flows. So we have a total of 12 parameters to learn. The left figure shows the true and predicted dynamic with the learned kernel, and again, there is no difference in eyeball norm. The right figure shows the prediction error with the initial kernel in red and with the learned kernel in blue. And as you can see, the error drops by several orders of magnitude. Now, let us look at this other example in which the time series is three-dimensional and the solution of the Lorentz dynamical system. A vector-valued kernel is diagonal as before with the following diagonal entries. So it has 18 parameters to learn. We learn those parameters with kernel flows, and this figure shows the true dynamic and predicted dynamic for the 3 components of the dynamical system. And as you can see, there is no difference between them. Now, this method is not limited to synthetic problems. It also works for extrapolating weather/climate time series obtained from satellite data. But I will not cover this in this talk as it is an ongoing joint work with Argonne National Lab. So far the moral of the story is that kernel methods can perform well on extrapolation problems if the kernel is also learned from data. In the setting that we have just looked at, this translates into linear extrapolation can do well if you also learn the space linearizing your extrapolation problem. So for that right figure, linear extrapolation would fail in the original space, but it will perform quite well in frequency amplitude feature space if you had the ability to learn that space. Okay, so what I would like to do now is to cover the deep learning answer to our original question, which kernel to pick. And the motivation for doing so is that there is a growing interest in the CEC community in using neural networks to solve nonlinear and complex PDEs. Now, physics-informed neural networks are a prototypical example of such approaches. And the idea here is to replace the solution of a possibly nonlinear PDE by the output of a neural network, and then minimize the following optimization problem to identify the parameters of the neural network. Numerical experiments have shown that this approach can work well on complex problems, but it can also fail on simple ones. Why? Well, the short answer is that pins are implicitly solving a ridge regression problem, that is a kernel regression problem, with a kernel learned from data, and that kernel learned from this optimization problem can be good or bad. To show this, we need to open the artificial neural network black box. And as a spoiler, what we're going to find in that black box is ridge regression with a kernel learned from data. And what I would like to do now is to show you what kind of kernel this is. I will do so in the setting of the following supervised learning problem, in which you try to approximate an unknown target function given f dagger of x equals y as before. So here, I assume the input-output spaces to be finite dimensional Hilbert spaces. And as before, I write x and y for the n dimensional vectors whose entries are the input-output data points, and I write f dagger of x for the n-dimensional vector whose entries are the images of the input data points under f dagger. Now, the ridge regression solution to this problem is to approximate the target function f dagger with the minimizer of the following variational problem, where this k-norm of f is the RKHS norm of f defined by some operator of vector-valued kernel k. And this minimizer admits the following representation formula. The artificial neural network solution to this problem is to approximate the target function with the composition of nonlinear functions, which we write f1, fd. To define these functions, write x1 for the input space x, xd plus 1 for the output space y, sandwich the spaces x2, xd between the spaces x and y, and let fk be a function mapping the space xk to the space xk plus 1. For artificial neural networks, fk is typically the composition of a nonlinear activation function with an affine function. This activation function written A here is typically an element-wise nonlinearity such as ReLU, CeLU, or the hyperbolic tangent. The affine function is typically defined by the weights and biases of the kth layer of the neural network, and these weights and biases are identified by minimizing the following empirical loss, defined as some distance between f of x and y via stochastic gradient descent. Now let us focus on the variants of ANNs achieving the state-of-the-art in industrial applications. These are the residual neural networks known as ResNets, introduced by her and others to facilitate the training of very deep networks. So the ResNet solution to our original problem is to approximate the target function f dagger with the composition of d functions, which we write capital F1, capital Fd. Each capital Fk, which we call a ResNet block, is the composition of the function little fk, mapping the space xk to the space xk plus 1, with the composition of lk functions mapping xk to xk. Each lowercase fk is, as before, the composition of an activation function with an affine function, and each one of these lk functions mapping xk to xk is the sum of the identity operator and a function vk mapping xk to xk obtained as the composition of the activation function with an affine function. And as before, the weights and biases of all these functions are identified by minimizing the following empirical loss, which is a quadratic loss on the mismatch between f of x and y. Now, as observed by Haber and others, the following function appearing in each ResNet block can be interpreted as a discretized approximation of x1, where x of t is the solution of the following ODE, defined by the activation function A and some time-dependent weights and biases to be identified as before by minimizing some empirical loss on the mismatch between f of x and y. Now, motivated by the structure of ResNets, let us consider the following variant of ridge regression, which we call mechanical regression. In this variant, we approximate the target function with the composition of some function f mapping the space x to the space y and some deformation phi L of the input space x. This deformation is written as the composition of L functions. Each one of these functions is the sum of the identity operator with a displacement Vs mapping x to x. Then this function f and this displacements vs are identified as minimizers of the following variational problem, in which these are the RKHS norms of the function f and the displacements vs, defined by some given operator-valued kernels k and gamma. Note that k allows us to regress functions mapping the space x to the space y, and the kernel gamma allows us to regress functions mapping the space x to the space x. Now, if you choose the right kernels k and gamma, then you can show that the regressor f composed with phi has the exact structure of one ResNet block with parameters obtained by minimizing an empirical risk with L2 regularization on weights and biases. And this is what these particular kernels look like. They are essentially defined as the product of scalar valued kernels and the identity operator on x and y. The scalar valued kernel is identified by its feature map varphi, in which A is an activation function and 1 is the constant function 1, which can be interpreted as an always active neuron. And again, under this particular choice, the resulting regressor has the structure of one ResNet block, where W tilde and the WS are the weights and biases of that network, and the previous variational problem is equivalent to minimizing an empirical risk with L2 regularization on weights and biases. Okay, now let us turn to the general case in which the kernels k and gamma may be arbitrary. And again, this general case includes ResNets as a particular case. Then we have the following theorem. As L goes to infinity, so recall that L is the number of layers in the network. As L goes to infinity, the adherence values of the regressor obtained from mechanical regression are of the form f composed with phi, where phi is the flow map defined by this vector field v, and v and f are identified as minimizers of the following variational problem. So an immediate question is, what kind of optimization problem is this? Well, it looks like an image registration problem. Now, recall that the kind of question that you try to answer in image registration is how to best align an image I with an image I prime. And this is done by minimizing the following variational problem, in which phi is a deformation of the coordinate system of the first image obtained as the flow of the vector field v, identified by minimizing the following variational problem, in which the first term is penalizing the lack of regularity of v, and the second term is a L2 distance between the deformed first image and the second image. Now, there is a variant of image registration known as landmark matching, in which you place a finite number of material points or landmarks on both images, and you replace the L2 distance between the deformed first image and the second image by a L2 distance between the landmark points of the first image displaced by phi and the landmark points of the second image. Now, observe that the variational problem that we have obtained as the limit of mechanical regression looks like an image registration variational problem with a few differences. And these differences are as follows. The support of the images I and I prime is no longer the unit square, but the input space X for the image I and the output space Y for the image I prime. And those images mapping the unit square to grayscale intensities are replaced by high-dimensional functions I and I prime, mapping the input-output spaces X and Y to some abstract space F, which is related to the space of forms introduced by Plato. And I can tell you how if you ask me that question at the end of this talk. The landmark or material points xi and yi are no longer points in the unit square, but there are data points living in the input space X for the input data points Xi and the output space Y for the output data points Yi. And we are no longer deforming the unit square or an underlying image or function mapping the unit square to grayscale intensities, but the input space X, which could be high dimensional, and an underlying implicit high dimensional function mapping the input space X to this abstract space of forms. Now, we will focus the presentation on the analysis of one ID registration block. That is the regressor obtained as the composition of F composed with phi, where phi is, as before, the flow map of this dynamical system with vector field V, and V and F are identified as minimizers of the following variational problem. Now, we have the following theorem, which essentially states that ID registration is ridge regression with a kernel learned from data. And this can be seen by observing that the ID registration regressor is equal to the ridge regression regressor with a kernel KV defined by composing the kernel K that appears here in ID registration with the flow map phi obtained with a vector field V, minimizing the ID registration variational problem. And an equivalent perspective on this point is that ID registration is equal to Gaussian process regression with a Gaussian prior learned from data. Now, one thing that we know about Bayesian inference is that it is brittle, that is extremely non-robust with respect to perturbations in the prior. Therefore, the identification of ID registration as ridge regression with a Gaussian prior learned from data implies the extreme lack of robustness of artificial neural networks. And this brittleness of ANNs has already been observed in image classification, and it is something to keep in mind when using ANNs in numerical approximation. Now, you can rigorously make ID registration and therefore ANNs robust by adding nuggets, that is multiple of the identity matrix, to the kernels K and gamma. And this is equivalent to replacing the ID registration variational problem by the following one, in which Q represents the trajectory formed by the input data set X as it propagates through the layers of the network. And these nuggets allow for some error or noise in that propagation. So we started this talk with 4 equivalent descriptions of kernel methods, and we are now going to finish it with 4 equivalent descriptions of ID registration. The RKHS description is the ID registration variational formula, which we have already seen. The kernel description is given by the following theorem, which provides a representative formula for minimizers of ID registration. More precisely, a minimizer V of the ID registration variational problem admits the following representation formula, in which Q is the trajectory defined by the input dataset as it propagates through the layers of the network. And this trajectory data space minimizes the following least action principle. Therefore, if we introduce the following momentum variables, then V is proportional to that momentum, and the position and momentum pair follows the flow of the following Hamiltonian system. This implies that V and F are uniquely determined by the initial momentum, and the norm of the minimizer is constant in T over the interval 0, 1. Now, if psi is a feature map for the operator valued kernel gamma, and if we rescale the momentum variables, then the previous Hamiltonian system is equivalent to the following one, in which alpha is a trajectory in feature space that is amenable to mean field analysis. Note that the representation of a minimizer V of the ID registration variational problem separates into the product of the transpose of the feature map, which only depends on X, and the trajectory alpha in feature space, which only depends on time. Finally, the Bayesian interpretation of the ID registration regressor is that it is a map estimator of the following stochastic process given the following information. Here, Xi is a centered vector valued Gaussian process of covariance kernel K. Phi zeta is the flow map of the dynamical system with vector field zeta. Zeta is a centered Gaussian process independent from Xi, defined by the following quadratic norm. And Z is a centered Gaussian vector independent from zeta and Xi with ID and 0 identity entries. Now, to finish, if we call ID registration block the composition of the function f with the deformation phi, then we can evidently compose these ID registration blocks by mapping the input space to a sequence of spaces layered between the input and the output space. And if we do so, and if we discretize this composition in time, then we recover exactly ANNs and ResNets. And if we do so with a particular choice of kernels for gamma and k, then we recover convolutional neural networks exactly. And I don't have the time to show you what these kernels are. And to conclude, the following list of references is relevant to this last part of this presentation, which is based on the following paper. And I will stop here. Thank you for your attention.
Thank you very much, Houman, for the